This video will continue going through section 7.5, talking about the binomial distribution. 7.5 also talks about a geometric distribution that we'll mention quickly at the end, but the vast bulk comes to this idea of the binomial distribution. I started to briefly introduce this at the end of the previous video, but we'll kind of start from scratch, re-explaining what this means, getting into the formula, and then we'll get several examples to see how we use this. So the first thing, a binomial distribution is a result of the binomial experiment. The binomial experiment is described on page 372 in your book. It starts off talking about a sequence of trials with the following conditions. Number one, we have a fixed number of trials. Number two, each trial results in only one of two possible outcomes, and we will classify those outcomes as one being success and the other being failure. Number three, the outcomes of all the different trials are independent, meaning every trial that we run, the probabilities of having success or failure remains exactly the same. Last, the probability that a trial results in a success the probability that a trial results in a success is the same for each trial. That really goes back to the idea of being independent. There's a little more to the idea of independence, that there's no overlap, but again, just reinforcing that every trial, the conditions are exactly the same. So if we have that situation, I'm going to jump right to the formula and then we'll re-explain what all the variables mean. And then I'll also demonstrate why this formula works the way it is. So if we have a binomial experiment, the probability, here we're using x as the number of successes. The probability of x successes is equal to NCX. We talked about that notation the other day. N is the number of trials that we're running, and that literally stands for N choose X. There's a few different forms of notation that gets brought up, but that's the main one that most books use. Our book, again, points out a few of the alternatives using factorials, but that's the one I'm going to stick with. So our formula starts with that. Then we'll get little p to the x power. Capital P is the probability that we're looking for in the big picture. Little p will be the probability of success in one trial, raised to, again, that's the same x that was here and here, to however many successes we want, times little q, which is the probability of failure, to the n minus x power. That is our probability formula. That's going to be the main piece that we use throughout this section. But before I get too deep into the formula, a couple other quick little things. We'll still have the ideas of mean and standard deviation. And the mean, in this situation, we're still going to see that idea of expected value. The average, the common, but a lot more in this context, we hear the words expected, the expected number of what we want, the expected number of what we don't want, but that idea of expected value. And this is a very, very simple formula here. This will just be n times p. And then for sigma, for the standard deviation, if we're looking at a binomial experiment, that will be the square root of n times p times q. Okay, one more time. What do all these letters stand for? Well, first off, the little n. N is the number of trials. One of the first things we said for a binomial experiment is that we know we are running a fixed number of trials, and we'll let n be that number. Then x will be the number of successes in n trials. We're running 7 trials and we want 4 successes. N would be 7, x would be 4. So x, again, my number of successes. Little p, the probability of success, but only in one trial. Little q will be the probability of failure in one trial. This idea of breaking this situation down into only two possible outcomes, these two will always be complements of each other. If I know the probability of success is 0.25, then I know the probability of failure is 0.75 because they have to add to 1. One of these two things must happen. So that's where I like to use this notation Q. The book pretty much always sticks with the idea of 1 minus P, because that is always the complementary relationship. Again, let's think of a different situation. Think about percentages. If there is a 90% chance that success happens, that means there is a 10% chance of failure. So using percentages, but the same idea. The probability of success would be 0.9, therefore you have a 0.1 left over for failure. And we could think of that just adding to 100%, or we could just use this formula. Okay, so that really gets through all the basic ideas. But before I just jump in and start solving some problems and seeing some good examples, I want to take this one extra step further. I want to show you why this formula works out the way that it does. So let's keep this kind of simple for this problem. I'm going to roll a 6-sided die. I've been using the dice situation, and here again, we're only going to roll one die. So I've been using this for a bunch of examples. Let's stick with that one more time. We're going to roll this die 3 times. What's the probability that in 3 rolls, I roll a 5 one time? Exactly one time. Just thinking about the basics of probability, we really have enough information to go through and answer this. Well, let's see. I'm rolling the die. I want a 5. So what in this basic situation, technically rolling a die has 6 possible outcomes, but all I'm focusing on is rolling a 5 or not rolling a 5. So in this basic presentation of a binomial experiment, we're talking about success, rolling a 5, and then rolling anything else would be considered a failure. So I like to actually start with that setup, thinking about when we start doing these problems, that's almost always where I begin. What are we calling a success? Therefore, we can establish the number of trials, and then we could start filling in the rest of the values and see what it is that we want. But again, I don't want to just jump right into this formula. I kind of want to use this example to see how this formula comes about, what this formula has going on. So thinking about this, okay, I'm rolling a die 3 times, so I'm going to set up almost 3 trials. But here's the thing. I want to get exactly 1 5. So if I roll the die 3 times, I get 1 5, and the other 2 times I do not get a 5. And that's where this complication starts, because maybe I roll the 5 first, and then the next 2 rolls, I get something else. And I don't even care what it is. I roll the 6, I roll the 1, I roll the 2, I roll the 4. All it's just that I'm not getting a 5. That gives me one possibility that satisfies what I'm looking for. Thinking about the basics of probability, how many outcomes satisfy, out of how many total possible outcomes, well, this is an outcome that satisfies. But it's not the only one. I could have the first roll is a not 5, then the second is a 5, and the third is a not 5. Or I could have the first is a not 5, the second is a not 5, and the third is a 5. But that covers all the possibilities. If I'm rolling a die 3 times, and I only want to get exactly 1 5, that covers everything. But now let's look at the probability that each one of these things happens. Starting with this one. Well, I roll and I need to get a 5. Well, there's a 1 out of 6 possibility I get that 5. But then the next 2 not getting a 5, again, there's the idea of the complement. I could think basically, well, there's 1 5, so there's 5 not 5s. Or I could just use that idea of complement. 1 out of 6 gives me what I want, means 5 out of 6 does not give me what I want. So 1 out of 6 for the 5, then a 5 out of 6, and another 5 out of 6. Multiply these 3 results together. Fractions or decimals doesn't make a difference, everybody. I'll leave it as fractions. 1 times 5 is 25. And then 6 times 6 times 6 is 216. So that is the probability that exactly that happens. But what about the probability this happens? It's almost the same thing. It's just I'm getting the same probabilities, but they're in a different order. I'd start with the 5 out of 6, then get the 1 out of 6, then get another 5 out of 6, right? 5 out of 6 for a not 5, 1 out of 6 for rolling the 5, then another 5 out of 6 for another not 5. And if I multiply these three, I get the same thing. And one more time, still a little different because they go not 5, not 5. So probability of not 5, another probability of a not 5, and then probability of a 5. But notice what happened. Every single one of these satisfies rolling exactly 1 5, and every single one of these has the exact same probability. Each of these satisfy. There is no overlap here, so we don't have to worry about intersection. So I would add this probability for each one of these. So I'd get this plus 25 over 216 plus 25 over 216. They already have a matching common denominator, so I end up getting 75 over 216 as the final probability. And now let's work backwards and see what happened and why this formula works the way it does. Because in every single one of these, when you multiply, the order you multiply doesn't matter. Multiplication is commutative. So if I just play some games here, every single one of these I could work into 1/6 to the first power, 5/6 to the second power. And I have 3 of those, so a 3 out in front. And this is where some statistics books do spend a little more time on counting. So some books have established this idea a little bit more. But that 3, that is the result, the 3 of these outcomes that satisfy one roll of 5 in 3 rolls, that comes from the value of 3 choose 1. I'm rolling 3 times and I want to get exactly 1 5. It doesn't matter with the order if the 5 comes up first, second, or third. Every one of these satisfies 1 5 out of 3 rolls. So what I just did was take the very, very long way, and after I got that answer, I went backwards and pointed out, if you do this, you get the exact same thing. And this is the use of the binomial probability formula. So again, trying to get a little demonstration. If we're going to now treat this problem, recognize that it is binomial, well, the first thing to realize, we're asked for probability. So we think about our probability facts. But as we start looking, we realize this is a complicated situation, and we recognize that it is binomial. So we would go backwards and start breaking it down. Well, how many trials? Every time we roll the die, that is a trial. So there are 3 trials. N is 3. What do I want? Well, I want exactly 1 5. So I say rolling a 5 is a success, and I only want to get 1 5. So the number of successes is 1. X would equal 1. Well, what is the probability of success? Since rolling a 5, and again, this always goes in 1 trial. I want the big picture of getting the probability after several trials, but inside of that, I need to think just in 1 trial. So what's the probability of success in 1 trial? Well, what's the probability of rolling a 5 in 1 roll? 1 out of 5. I'm sorry, 1 out of 6. So little p is 1 out of 6. Well, if rolling a 5 is a success, then rolling anything else is a failure. So what's the probability of failure in 1 trial? That's the 5 out of 6. That's the Q. And then just look at my exponents. This was the X. We already established X was 1, so that went here. And then we already knew N and X, so N minus X, 3 minus 1 gave us the 2. And now this certainly, if you're going to use your calculator, we can convert back to having this fraction. But if we put this in the calculator, let me start off with the 3, math, to the PRB to get the NCR button. 1 times 1 divided by 6 to the first power times 5 divided by 6 to the second power. Again, little options, raising something to the first power. Well, you know, that's really just itself, so you can kind of skip that. There's a few little things that come up, but overall, that's just a very literal interpretation of what I have here. I hit enter, I do it all once, I get a decimal, rounding off, I'll go 0.347, and now let's just quickly confirm. Not a surprise when we did it as a fraction that we're getting the same thing the calculator gave us as a decimal. So again, let's move on. Let's start seeing a few more problems. So my second page, let's jump in. This was page number 1. Let's start looking at a few examples. Let's start off with an example based off of quality control. Okay? We receive an entire shipment of computer monitors. We test 10. We're not going to test every single computer monitor that we receive. We're going to test 10 of those computer monitors. We test 10. If more than one of the monitors is defective, we reject the entire shipment. It's estimated that 3% of the monitors have a defect. So I'm going to ask several questions here. Number 1, what's the probability that they reject the shipment of monitors? And then number 2, we'll do what's the probability they accept the shipment of monitors. So there's a lot of information here. Let's take our time, let's go through it. We see when we get down to the question, and we kind of pointed this out earlier, we're kind of at a place in the class. Pretty much all of our problems have a lot of general description. So just kind of reading through, what am I looking for? Well, I got to read through, but eventually I start getting questions about probability. Well, how am I going to find this probability? Well, again, thinking about our experience, what have we done? What do we know? Well, we look at this and we can realize that this is a binomial situation. We're testing a bunch of monitors. So every time we test a monitor, we're running a trial, and that we're looking for defective computer monitors. So I'm just going to put a bunch of notation down at the bottom, and then I'll come and fill in for each of these 2 problems. So with this basic setup, and this is what's a little weird. I wanted this as a first problem, so that way we have to read into this a little bit. My next problem will be a little bit more literal. But here, the probability they reject the shipment, that means that we had more than one defective monitor. So it looks like we're focusing on defective monitors. And this is another reason why I picked this one, because when we use words like success and failure, there's already this connotation that success is good and failure is bad. But in any situation, we can make whatever we want success or failure. The previous one, a 5 is what we wanted, so rolling a 5 was a success. Anything else was not what we wanted, so we call that a failure. So with this setup, it seems weird, but a defective monitor, before I start filling in some numbers, let's just get the idea out here that we're calling one defective monitor is what we are defining as one success. Okay, I started off defining, literally putting some words, and a lot of people, we don't have to write that out, but we have to think about it. What are we classifying as a success? Now I can start thinking about all the different values that I need to find. So now with that setup, N, well, how many trials are we running? Well, we're testing 10 computer monitors. Each one of those would be its own independent experiment. Okay. Next, okay, I know what one success is. How many successes do I want? Well, more than one defective monitor. So if I look at this problem, more than one defective monitor, X is literally more than one. Well, thinking about that would be, well, if there's 2 defective monitors, or 3, or 4, this doesn't keep going forever because we're only checking 10 monitors. So up to 10. Okay. How about little p? What is the probability of success in a single trial? What is the probability that one monitor is defective? Well, let's come back up here. If 3% of the monitors have a defect, that means the probability that one is defective is 0.03. Be careful here. This is so easy to take 3% and make that 0.3, but that would be 30%. So be careful with that. 0.03. 3 out of 100 is our 3%. Well, if 3% are defective, that gives me success. That means 97% of them work the way they should. So the probability of failure, which failure would be finding a monitor that works fine, would be 0.97 here. So now, all of that is the setup for problem number 1. And now you're probably already wondering, how am I supposed to handle all these X's? But let's take one quick moment and jump into section number 2. What's the probability they accept the shipment? Well, if they reject the shipment, if we have more than one defective monitor, well, if we have 0 or 1 defective, that means they would accept the shipment. So in problem number 2, all the rest of this is the same, except X is now only 2 possibilities, 0 or 1. So I'm actually going to start with this. Even though this was problem number 2, and after we finish this, I'll point out, this will be a very nice shortcut that gets us to problem number 1. So focusing on problem number 2, how am I supposed to know the probability that X is 0 or 1? These are separate outcomes, and there's no overlap. So this goes back to one of our earlier probability ideas, that if these events are independent, that I could just find the probability of each one separately and add them together. That's what I'm going to do. That will be the work that solves problem number 2. So all of this again went with number 1. Same bit of information, but just the different X goes with number 2. So I'm working on this one. What's the probability of 0 defective monitors? 10, choose 0, 0.03 to the 0 power, 0.97 to the 10th power. I did that a little fast. The more you use this formula, the more easy it is to just quickly start plugging things in. How many am I running? How many do I want? Probability of success to how many successes, probability of failure, the n minus x, how many total trials minus the number of successes, that's the number of failures. So in this one, I wanted no successes, no broken monitors, and all of them I wanted to work properly. So I'll do this on my calculator. And this happens to be a funny one. The 10 choose 0 happens to be a 1. Anything to the 0 power happens to be a 1. So that's just a coincidence. So nice thing to realize, but we don't want to go too nuts with that. And again, typical rounding. Let's get a bunch of decimal places and we could round at the end. So I'll get 0.7374. I took 4 decimal places, looked at the 5th to round to the 4th. But I'm not done, because now I need the probability of 1 defective computer monitor. So that will be 10C1, 0.03 to the 1st, 0.97 to the 9th. Again, you have take-home exams, so you have plenty of time to do this on the calculator. Be careful, be methodical. Notice, even it's not just this calculator, even a lot of your other scientific calculators still have a view screen, so you could do all this work at once. If you start going too slowly, again, just more possibility, little places to round incorrectly, to accidentally miscopy a decimal. So again, a good thing to try and do this all at once. So I get 0.2281 if I round to the 4th decimal spot. And now I'll finish. So what's the probability that they accept the shipment? This plus this. And now, I mean, there's no problem keeping the 4th decimal place, but now if you wanted to go down and round to 3 decimal places, this is where we should do most of our rounding at the very end. So I'll go to 3 decimal places, 0.966. That is a probability very close to 1. So it is a very, very strong possibility that they will accept the shipment. So far, so good? Again, everybody, this is really how quality control works. That any type of product, that anybody who actually sells these products, that they have to test some of them to make sure they work, but we can't test all of them, so they just test a bunch. And we have some of these little numbers to have a good, accurate idea of how close that means that all the products will work well the way they're supposed to. Okay, so a good first problem, and even though that was technically number 2, it really, really helps getting to number 1. Even if I never asked this, that's the secret. If you look at problem number 1, it's all the exact same work, but look at how many x values that there are. There are 9 x values you have to go through. So you'd have to do this formula 9 times, add the results together. So even if I didn't ask question number 2, it would have been my advantage. Because in the big picture, in the small picture, 1 computer monitor works, 1 computer monitor doesn't work. That's a complementary situation. But in a larger picture of testing 10, either more than 1 computer monitor is defective, or 1 or less is defective, and these two form the complementary situation. So you could do probability of 2 plus probability of 3 plus ... plus probability of 10. Again, do this every single time and add these together the way I did this twice and added those together here. Or take advantage of the work we did here. Realize there's only a couple of x's in this situation, so let's find this probability and use the complement. Because in the big picture, testing 10 monitors, in the end, there's really 2 results. They reject or they accept the shipment. So once we figure out the probability of accept, 1 minus that will give us the probability they reject. So definitely a tough problem. Kind of jumped right in, got into something that was a little tough. So if that was a little bit much, let's see a couple more. Definitely come back and consider this again. In your homework, the book likes to do these things too. Very often they ask a couple of questions, and how oftentimes, not every time, but there are some of these problems where it's kind of like the answer from number 2 helps you with number 1. Or vice versa. If I had gone through and did all this work and got this, then I wouldn't have needed to do this. I could have done 1 minus the 0.034 and got the 0.966. Okay, just one very, very quick thing before I move on. If you go back to that front page, we said this was definitely the main highlight, but I had these on the side as well. So just quickly, the expected number and the standard deviation. And especially if I tested more, if I was going to test 1,000 computer monitors, what's the expected number of defective? What's the standard deviation for the number of defective computer monitors? This is what you will use. And I'll bring that up in our next problem. So let's continue. Let's now look at, this will be page 3. And now let's take a look at this. We'll get a little information. A recent survey found that 2 out of 3 people don't think the government does enough to fight to help homelessness. So we're just getting some information. So out of the next 8 people, I'm going to ask a couple of quick questions here. Number 1, what's the probability exactly 6 of them think the government doesn't do enough? Again, to help the homeless. So what's the probability exactly 6 of them? Number 2, we'll do what's the probability at least 6 of them. Again, same thing, I'm just abbreviating. What's the probability at least 6 of those people think the government doesn't do enough to help the homeless? And then last, number 3, what's the probability fewer than 6 of the people think the government doesn't do enough? Okay, so again, a lot of information, but all these questions again boil down to probability. Well, what situation? We're talking about, do people think the government does enough to help homeless? And we're kind of focusing on people who think that the government doesn't do enough. So, well, 2 situations. Either they think the government does enough or they don't think the government does enough. We're focusing on not doing enough. So I will define one success as one person who believes the government doesn't do enough. That is what I'm defining as a success. Finding a person who believes the government doesn't do enough. Well, how many people am I testing? If finding one of them is a success, how many trials are we running? Well, we're going to look at the next 8 people. So n would be 8. How many successes do I want? Well, in question number 1, the probability exactly 6 out of those 8 people think the government doesn't do enough. So x will be 6. Little p, what's the probability that they don't think the government does enough? Well, a recent survey found 2 out of 3 people don't think, so the probability that they don't think the government does enough would be 2 out of 3. Well, then little q would be 1 out of 3. If 2 out of 3 think the government doesn't do enough, that would imply 1 out of 3 thinks the government does do enough. There's the basic complementary situation. And that's it. This one was a little more friendly. I really emphasize the word exactly here. And the book kind of does that a little bit as well. But if it just said the probability 6, well, the exactly part is implied there. We'll see in questions 2 and 3, the at least 6, the fewer than 6. That'll bring up a few little extra tidbits. But this is all the work for number 1. Everything is well set up here. And again, there's only one x value. So this will just be using the problem, the formula one time. The probability 6 people think the government doesn't do enough will be 8C6. 8 was the N. Choose, the C is always there just as part of the notation. And 6 is how many successes we want. Times 2/3 to the 6th power times 1/3 to the 2nd power. I wanted 6 successes, therefore I wanted 2 failures. Okay, tiny little things. If you just go backwards for 1 second, here our little p and our little q were decimals. Here the p and the q were fractions. Doesn't matter, everybody. Fractions or decimals, probabilities, we could do it either way. Some people always like to make them decimals, so they think it's a little easier to plug in the calculator. But that's why I intentionally chose this one, because if you put 2/3 as a decimal, you get 0.6 repeating. So again, just one of those situations. Instead of rounding that off, just stick with the fraction. It'll just be a little bit better, less possibility for any rounding mistakes at the end. But that's it. We've got everything set up. Now I just do the work in the calculator. 8C6 1/3 raised to the 6th power. Oops, I'm sorry, that was 2/3. 2/3 to the 6th power, and then 1/3 to the 2nd power. These are still probabilities, everybody. If you start getting something like 2.5, something's wrong. Okay? If you start getting a negative answer, something's wrong. These are still probabilities. It's a bit of an ugly formula, but at the end, these probabilities should still make sense. And maybe we have a little sense of like, well, how realistic is that? Should that be a probability closer to 0 or closer to 1? You know, we may have some instincts, but we're really leaning strongly on the calculator for the computation here. So this would be, and this is the final answer, everybody. So I'll just round to the 3rd decimal. 0.273. If you want to put 0.273, of course, that's fine, but 0.273 is the answer to number 1. Okay, what's the big deal? What comes up in number 2? Now we want the probability at least 6 out of the next 8 people think the government doesn't do enough. So what's the big difference in problem number 2? It's X. We're still testing 8 people. We're still defining the same success and failure, so these probabilities haven't changed. But that's where the at least comes in. At least 6. If you need at least 6 people, well, what satisfies? Well, getting 6 people would satisfy, but so would getting 7. So would getting 8. I'm not going to go more than 8 because I'm only testing 8 people, but that's the idea of at least. If you need at least a 65 to pass the exam, well, getting a 65 or anything bigger will pass. So that's the big thing, just to pay attention to those extra words. So at least 6. Now I've got 6, 7, or 8. Well, I already did the probability of 6, so let me do the probability of 7. 8C7, 2/3 to the 7th, 1/3 to the 1st, and the probability of 8, 8C8, 2/3 to the 8th, 1/3 to the 0. I know I went through that a little quickly, everybody. Take your time. Make sure go back, plug those in, but I'm just trying to get to the answer here. So now I'll get each of these. Again, there are little shortcuts that some people know. Some people, they really like to take advantage of the second enter button to go back, so that way they don't have to retype everything. They could just go change little individual values. So there's a few little things some people realize, but again, I'm just being very methodical, typing everything in. So I get 0.1561. And then similar down here. I get 0.039. But the final answer for number 2, I need each of these probabilities added together. So I'm going to finish with oops, sorry, miscopied. This, the 0.273 plus 0.156 plus the 0.039 for a final answer on number 2 of 0.468. And now last but not least, number 3. Now we want the probability that fewer than 6 people think the government doesn't do enough to fight to help the homeless. And that is, again, the complementary situation. Fewer than 6, well, that would be 5 people, 4, 3, 2, 1, or 0. I can't have negative people. And don't forget, 0 is in this list. A lot of people have a bad habit stopping at 1, but 0 out of 8 would still satisfy fewer than 6. And again, I could be very slow about this. Similar to number 2, I had 3 x values, do the formula 3 times, add those results. And here I could do the formula 6 times. But this is a good situation to realize the complement, that these two situations are complementary, that every x value is covered between these two. So instead of doing this 6 times and adding them all together, I'll do the shortcut, 1 minus the probability that we had for number 2. And this is another good situation. Instead of doing these 6 x values, even if this wasn't asked for, it would have been shorter to just do these 3 and then to use the complement. So 1 minus the 0.468 is 0.532. Okay, let's finish up with one more problem like this. So, this last one, let's say we have a city, we have a rainy city, a city where it rains a lot. In fact, in a particular month, it rains 85% of the days in this particular rainy city. So with that information, in the next week, which again, for our week, we'll consider 7 days. And we'll have a few questions here, but I'll start just in the next week. What's the probability it rains exactly 5 days? Notice I said it rains exactly 5 to emphasize, but I don't need the word exactly. Because, hey, what's the probability it rains 5 days? Without any other word, that's all exactly what it means. Exactly 5 days. Okay, well, what's our situation? Well, the rainy city, we're talking about it raining 5 days. Let's declare our success that it rains 1 day. With that definition, well, how many experiments are we running? Well, we want it rains 5 days in the next week over the next 7 days. N would be 7. That's how many trials, how many experiments we're running. How many successes? Well, I want it to rain exactly 5 days. X would be 5. What's the probability of success? Well, if it rains 85% of the days, the probability it rains 1 day is 0.85. And then the probability of failure, the probability it does not rain, well, if it rains 85% of the days, that means it does not rain 15% of the days, or again, can always just do that 1 minus relationship. 1 minus the 0.85 to get the 0.15. So not bad. Exactly 5 days, only 1 x value, everything set up. Just jumping right in. So this probability that it rains 5 days, 7c5, 0.85 to the 5th power, 0.15 to the 2nd power. And again, I'll take a few decimal places here. Let's go to the fourth decimal this time, 0.2097. And that answers this question. Well, let's play some games. What's the probability it rains more than 5 days? Well, now x would be 6 or 7. And more than 5 does not include the 5. If I said the probability it rains at least 5 days, now I'd have x as 5, 6, or 7. But just more than 5, well, now x is just 6 or 7. So now we'll use the formula twice. I'm just going to do a lot of arithmetic. You can write it out. I'm just do the work. And again, the better you get with this, I recommend for your test, it's a good idea to write the formula just in case there's any goof on the computation. But just notice with practice, you should get very accustomed to it. 7, choose 6. I'll get the 0.85 to the 6th power and the 0.15 to the 1st power. And the probability of 7, 7 choose 7. 0.85 to the 7th power, 0.15 to the 0 power. Add these two together. So there's the probability it rains more than 5 days in the next week. And last here, I'm going to throw an extra part in, but just one more like this. What's the probability it rains no more than 5 days? Just all these little words. That's one of the biggest things. A lot of people, the initial experiment is a little tricky, but getting used to the values and plugging in. But then once they get past this part, it's just getting to that second part. When is there more than one x I need to test? That a lot of people, they see 5 and they treat this question exactly the same way they treated this question, and they ignore words like exactly, at least, less than, more than. So just to be careful with that. Now, no more than 5, well, that's 5 or fewer. Now x would be 0, 1, 2, 3, 4, or 5. And one more time, we could take advantage of the complementary situation. All of these x's are all possibilities except for these two, so that these two are, again, big picture complements. So 1 minus the 0.717, and there is the answer. So again, I really tried to reinforce the big picture complement, but I also tried to give you some good practice, getting the language, the less than, greater than, at least. And now just 2 more quick things to wrap up this video and to finish this section. Let's still stick with this. Now let's go over the next month. So, and we'll have 30 days in this month. So over the next 30 days, what's the expected number of rainy days, and what's the standard deviation? For the number of rainy days. Long, hard way. We see that idea of expected number, that's the idea of average, of mean, and then standard deviation, no hiding that. And if we just treat this like the plain old probability distribution, well, we'd have to make the whole table. What is x? What is p of x? And over the next month, you'd have 30 days. And every single one of them is possible. Maybe it rains 0 days, 1 day, 2 day, 3 day, 4 day. You go all the way up. X can go from 0 to 30. So just making your XP of X chart would be a lot of work. You'd have to use this formula so many times for each one separately. And then after you make that whole huge table, then you have to use those old mean and standard deviation formulas. So that, if we didn't learn anything new about binomial, that's a problem we could handle from the earlier sections, but it would be a nightmare to go through. But now all we have to realize that, again, it's still binomial. We still have the same setup. We're looking at a success is a rainy day. So what's the expected number of rainy days? We'll just use mu is n times p. We're going to look at the number of days, the number of trials, which is 30, times the probability of success, which here would be 0.85, and that's it. Such a simple formula, but again, only works because we knew it was binomial. And the 25.5, again, for any real computation, we'd keep it. So we'd have 25.5, or about, again, 26 rainy days out of the next month, out of the next 30. For standard deviation, well, I just get the square root of NPQ. So my n is 30, my p is 0.85, my q is 0.15. Again, the only thing that changed when I moved down here was just going to the next month instead of the next week. Just that n, the number of days, changed. But my p and my q values are the same. This looks a little bit uglier, but still nice and easy on the calculator. All at once. Square root. I've got 30 times 0.85 times 0.15. I use the times instead of the parentheses here. You notice earlier I was using the parentheses just like I did in the formula. I use that on the calculator. You could use the times button there. Some people, when you start getting the fractions instead of the decimals, they prefer the parentheses. But again, a lot of little options just to make sure we're multiplying correctly. So that's correct. The square root, most calculators open a parenthesis. It's a good habit to close it at the end. So 1.96 rainy days, about 2. And we could still always go back. So what does that mean? Well, with this mean and this standard deviation, 2 above, 2 below, that's basically the ballpark for what we should really expect, what would really be common in that situation. Very, very last thing to say. No more work to go with this, but I just want to point out that in this section was trying to focus on some discrete probability situations. And not all discrete situations are binomial. We went through a lot talking about what is the binomial experiment, but it happens a lot. It comes up often enough, it's a big section, and it really helps us with a lot of probability problems. So, not the only discrete distribution. The book also talks about a geometric distribution, but we're not going to do any problems with that. That would be a situation where how many times will something repeat before it changes? So if you're a basketball fan, what's the probability LeBron makes his next 6 free throws, but then misses his 7th free throw? That would be a geometric problem. Or vice versa, if I had someone who missed a lot of free throws, what's the probability they missed, or not even free throws, just what's the probability they missed their next 8 shots, but then make their 9th shot? That would be something we could do with the geometric distribution. You could do that with baseball and thinking about, well, what's the chances he does not get a hit in his next 6 at-bats, but then gets a hit in his 7th? Or so many other situations. What's the probability that my bus arrives on time the next 5 days, but then is late on the 6th day? So a lot of situations, that would be geometric, just another example of a discrete. The next section will look at the normal distribution and get one good example of continuous probability distributions.